Alrighty, so let's go ahead and do problem number 3. It says after the bumper cars hit, oh no, they fall into this pillow, and we wanted to talk about what the pillow's purpose is. A lot of you wrote that the pillow cushions the fall. I know that it cushions the fall, but you need to talk about why cushioning actually matters in terms of impulse and momentum. So specifically what we have is, we have that Ft equals mv final minus mv initial. Now here's the thing, whether you have concrete or a pillow, this is the same. This is the same for pillow or cement. And of course we don't want a kid falling on cement. So here's actually what happens. What happens is the pillow increases time and the force actually decreases. And what actually means here, what this actually means is the impulse is the same. And what happens is we reduce force by increasing the time. And that's the key. That's the key to doing this problem. So these are the graphs. I'm sorry they're drawn so badly, but this is what you were given, and you're expected to figure out what the position graph or the acceleration graph. You're supposed to fill in the appropriate graphs on this problem. So I'm going to go ahead and do that now. So for this first one, we're actually going to start off slow going backwards. We're going to start off fast going backwards, and then we're going to slow down, and then we're going to speed up going forward. So it should actually look like this. And since the slope of the velocity graph gives us the acceleration, we're just going to get a line like that. Now for this next one, we're actually going slow backwards, and then we speed up, and then we're going fast backwards, and we slow down. And so that means our acceleration, being the slope of the velocity graph, looks like this. So these are the graphs that you should have got on your final. So we're still in the Ghost Blaster situation, and let's just remember that the Ghost Blaster plus the young children, they have a combined mass of 160 kilograms. And of course what this means is that the force of gravity, the Earth pulling down on them, does so with a force of 1600 newtons. So let's put all that together. And you know what? I made a little bit of a mistake in the previous problem. Whoops. It actually turns out that the force that we are generating here in this problem right here, I said that the friction force was 480 newtons, and that's false. 1600 times 0.4 actually gives us 640 newtons in the previous problem. So I apologize for that, and you'll see that in the next vid, or in the previous vid. Now continuing with this one, we're going to have this motor starting up, working at partial power, but now the person's still pushing. So let's just figure out. We're going to have the normal force. We're going to have the weight. We're going to have this pushing force. And we're going to have the friction force. So let's go ahead and set things up. So I'm going to have the normal balances the weight. And so that means that I'm going to go ahead and get the normal force as 1600 newtons as before. And the friction is mu times the normal force. And now we're going to get 1600 times 0.3 is 480 newtons. Because that's 0.3. And so let's set up the equation. So we're going to have the pushing force minus the friction equals m times a. So we're going to have 900 total minus the 480. And that's going to give us 160 times a. So we end up getting actually 420 newtons equals 160 times A. And A ends up being, I think, a little over 3.5. Let me just double check that, though. So 480 divided by 160, 420 divided by 160 actually gives us 2.6 meters per second squared. And we want to know how long it'll take the car to move from rest to the exit. So how long means how much time. It didn't say how far, it said how long. That's like time. So that's going to be V equals AT plus V naught. So that's going to be 22 equals 2.6 T plus 0. And that's going to give us a time of about 8.9 seconds. So that's how we do problem number 7.